welcome to lecture 3. Before I begin, are there any questions from what we did in the last lecture? I think we essentially ended up proving the art gallery theorem. So, any confusion, any doubts? Okay. So, let me proceed with a new problem. It's a fairly simply stated problem, and it may not sound particularly useful. Nevertheless, I will use that problem.
Yeah. Questions regarding the art gallery.
Yes.
One is if the art gallery is a three-dimensional object, so what will be? What will be the number of? Is there anything known about the number of the?
Okay. So the question is that if the art gallery problem is posed in 3 dimensions, what happens? So clearly the problem becomes even harder. So there is no question of having a fast polynomial time solution. If you are asking about essentially the results about, do we have a tight bound like this one we have, I must confess that I don't know, and I doubt that there is any such tight result in the 3 dimension.
Another question is, suppose the art gallery is like it's like orthogonal, like to a normal gallery.
Yeah, that's how I pose the problem, as a orthogonal polygon, simple polygon. Initially I pose the problem like an orthogonal simple polygon.
Yeah, if that is the case, then in that case, is there the results are like in by is that any better?
No, the results remain the same. No, let me retract that. So the results may not remain the same for the simple reason that the lower bound construction, that is, you need at least so many. Okay, I'll take it back. So the result would differ by a small amount. Yes, I agree with that. If it is rectilinear polygons. Okay, so coming back to this new problem that I want to discuss today. So let me just give some kind of motivation before I pose the problem. So it's like this, suppose so people do own shares from different companies, right? And the shares are priced according to the market, and every day the price changes. Okay, so suppose there are 10 kinds of shares available, okay, and there are many people who own such shares, and the pricing, the cost of the price of the shares change every day, but on any specific day, depending on the price of the share, some person can claim to be the richest person, right? Depending on what the share, how many shares he has, how many share values, what is the share value, and so on and so forth. So then, if some person is the richest person one certain day, the next day again, because of the change in share prices, someone else could become the richest person. Right? Now, given a population, okay, if we want to keep track of the fact that who are the potential richest person, okay, what would you do? So what we do in the sense that who are the potentially richest person? So how would you approach this problem? So I am not trying to do any prediction. I am only trying to get a set of persons who could be the richest person on some day, depending on some values of the shares.
We would probably look at what their current revenue is, their assets are, and what can be the changes in future. So on the day we want, how much they can.
Okay. Let me give you an example. Okay, suppose there are these 4 persons. P1, P2, P3, P4. Okay, and let's say that only 2 kinds of shares. Okay, share 1 and share 2. All right. So person 1 owns, let us say, 100 shares of this, and let us say 50 shares of this. Okay, person 2 owns maybe 120 shares of this and maybe 30 shares of this. Okay, person 3 owns let us say 90 shares of type 1 and let us say 40 shares of type 2. Okay, person 4 owns, let us say, 115 shares of type 1 and 20 shares of type 2. Okay. Now, the value of a share is unpredictable. let us say, not known. On you can't even predict the future for future. Okay. So, if you have this kind of data, if you have this sort of data, then can you say anything about who could be the potentially the richest people? So, you are saying that P1 and P2. Why are you excluding P3 and P4?
Because P3 has 90 shares, 90 of share 1 and 40 of share 2, but P1 has got more shares than him in both.
So, whatever be the price of the share on a certain day, P1, because it has more shares of both types than P3, okay. So, that person, whatever be the share, will always kind of be richer than the person 3, okay. And likewise, the number of shares owned by P2 of each type exceeds the number of shares owned by P4 of each type, and therefore, on any particular day, whatever be the value of the share, P2 will always be richer than P4. So, therefore, P4 and P3 are certainly not among the potential richest person, only P1 and P2, and depending on the price of the share, maybe on a certain day P1 is richer than P2 or vice versa. Okay. But then certainly P3 and P4 cannot claim that position on any day, because they have fewer shares of any type than another person in the set. Okay. So, this kind of relation, okay, so I have discussed only with respect to two kinds of shares. So, I can if I draw this in a as a graph, okay. So, let us say this is share 1 and this is share 2, okay. So, let us say some 10, 20, 30, 40, 50, 60, let us say about 100, okay. And here we have 1, 2, 3, 4, 5, let us say up to 50. Right. So, I can actually plot this. Okay. So, person 1, okay, has 100 shares of type 1 and 50 of type 2. So, person P1 is a point here. Okay. Person 2 has let us say x coordinate 120 and y coordinate 30, right. So, somewhere here and 20. Okay. Person P3 has 90 as x coordinate, okay, and 40, right. So, it will be somewhere here. Okay. The P4 has 115, okay, and only 20, right. So, just a moment. So, no 150. So, I am sorry. So, this was incorrect, that was 30, right. This is 30. So, 100 and P2 is 120 and 30. So, it is about here. This is P2, this is P1, this is P3, and P4 is 115 and 20, right. So, somewhere here this is P4. Right. Okay, sorry, the example is that all the points are clustered on this end. Now, geometrically, what is happening is if you look at P1 and P3, okay, both coordinates of P3 are smaller than P1, right, and both coordinates of P4 are smaller than P2. Right. So, this relation where both coordinates are smaller, we have a name for it. So, we say it dominates. Okay. So, we say Pi dominates Pj xi is greater than xj and yi is greater than yj. Now, there is of course, this thing that what happens if it is equal to, let me ignore it for the time being, let us not get into that. It can also be taken care of with appropriate definitions. So, let us say we are only have these inequalities. Okay. So, only if it, so Pi dominates Pj only if and only if both coordinates of the ith point dominates the dominates the coordinates or is greater than the coordinates of the other point. And this, of course, this definition extends to higher dimensions, where you can have in a 3 dimensions. So, depending on how many kinds of shears it has, this d kinds of shears, you go to d dimensions to express the same information. All right. So, then what is this problem about? So, this problem is about the following, that given a set of n points. So, in the special case on a plane, otherwise in d dimensions, we want to identify, let us say call this set S, identify, let us say S prime subset of S such that for all points in S prime, there does not exist any point Q belongs to S such that Q dominates P. Right. So, those points form this subset S prime. So, that set of points. So, in the given example, P1 and P2 basically comprise that set S prime. So, because P1 and P2 they are not dominated by any other point. Right. So, this is what we are calling this S prime, and the name for this set S prime. So, S prime is called the maximal set of points. No, it is not dominated by any other point, right. So, why are you saying only S? So, the question is that why have I chosen Q to be in S? It cannot be dominated by any point in the set, not just S prime, sorry, S minus S prime. I can't let it dominated by another point, no way. So, a maximal point is the one that is not dominated by any point in the set, right. And the problem is, the algorithmic problem is to, given a set of n points, find the set of maximal points. So, problem, find the set of maximal points. So, that is the problem. That is a problem we would like to solve algorithmically, and of course, as with the algorithm as fast as possible. So, from the definition of the problem, what would be the straightforward solution? So, the straightforward solution, as someone just pointed out, is n square or whatever n choose 2. Why? I can take every pair of points and find out if one point is dominated by the other. Any point that is dominated by another point cannot be a candidate for the maximal, and it gets thrown out. So, any point that survives all these tests will be maximal, and clearly at least one point must be maximal, right. The point having the highest x coordinate, points having the highest y coordinate, those points must be and it can be the same point, right. So, what I am saying is that essentially your set could be like all the points are here. So, this is the only maximal point. That is one extreme. Another could be that I have things like this, right. So, it is kind of looks like a staircase. So, all these points must be maximal because they are not dominated by each other, right, and any other point inside this staircase not maximal clearly. So, this is this also the structure of the solution, right. I mean, it is like a falling staircase in the increasing x direction. Just look at it carefully. So, you have any doubts that any other point inside the staircase must be dominated by at least one point, must have both x and y coordinates smaller than some other point in the set. So, for example, this point. Okay. So, this point and this point, clearly the x coordinate of this point and the y coordinate of this point is smaller than x and y coordinate of this point. Moreover, the x and y coordinate of this point is also smaller than x and y coordinate of this point. So, a point may be dominated by more than one point, but certainly it is dominated by at least one point, and none of these points in the staircase can be dominated by each other, because it is in the increasing y direction, x direction and falling y direction. So, this is the structure of the final solution, okay. And we want to essentially identify this, and the straightforward simple solution is take every 2 point, compare their x and y coordinates, and if one is dominated by the other, just throw it out. So, that is n choose 2. Well, that is okay, but maybe we can do better.
There is one solution, it can be done in order and log n if we can sort them in their x coordinates, and then take the point with the maximum x coordinate, and then start going backwards to point with the decreasing x coordinate, and until we find a point whose y coordinate exceeds this.
Yeah. Okay. So, I think you knew the solution because you have seen this problem before, right? If I am not wrong. It's obvious. Okay, fine. It may be obvious. Okay. So, okay, let me iterate the one proposed solution, which seems to be a nice and fast solution. So, you sort the points along x axis, okay, and then starting from the point with the largest x coordinate, right, we move left, i.e. in decreasing values of x. Okay. So, this is what we do. So, in this particular case, so suppose this is the highest x coordinate, okay, and there are many other points. There is a point here and a point here. So, what we do is, from here this is the next point that we must consider in the decreasing x coordinate. Now, because we are considering them in the decreasing x coordinate, we know that any point that we encounter later is already dominated on the x coordinate. Okay. It now is a question of whether or not the y coordinate is also smaller than this point. So, if it is so, okay, we discard this point. So, this point gets discarded. Okay. Then we move further and we come here. Okay. So, this has a smaller x coordinate than 1. Okay. Let us say this is 2, this is 3. So, but 3 has a larger y coordinate. So, 3 survives, and 3 will always survive because all other points have smaller x coordinates. So, no other point can dominate 3. Okay. So, this is the way we progress, and so what is the information that we require to maintain. So, when we are here, okay, I know that this point has a smaller x coordinate than all the points we have seen so far. Okay. So, the only thing that we need to find out if there is any of these points that we have seen till now has a larger y coordinate, which means that the only information that we need to maintain is the largest y coordinate of the points scanned so far. Okay. We are scanning from in the decreasing x direction. Okay. So, this is easily done, right. So, starting from the point the largest, we moved and maintain the value of the largest y coordinate. So, if the y coordinate, so okay, so let us call it something, say y max, okay. If for the current point P x, sorry, y of P is less than y max, then P is not maximal, else P is maximal. That is all. And what is the running time of this? Well, in step 1 we sort. Okay. So, sorting will take whatever time it does, let us say n log n if you are using comparison trees. So, this will take n log n, and then the step 2, which is the iterative step, we look at every point one after the other. What is the information that we maintain? Just the maximum y coordinate, y max. Y max may have to be updated. So, in fact, I missed out something here. So, else if else P is maximal, okay, which means that we must update. So, y max, okay, must now be set to the y coordinate of P, because that exceeds the previous y max. So, the only change that we have to make is this one value. Okay. So, it is basically constant amount of work for every iteration therefore, for all the n points, okay, we need only a total of. So, for each point additional order 1, okay, implying total order n. So, the whole thing is actually dominated by this n log n. So, the first step is the dominating step, I mean in terms of algorithmic complexity, and the second step is only linear time. So, if someone had given you these points in a sorted manner, then you would only need order n time, linear. Okay. So, nothing can be better than linear, but of course, the first step is n log n. Can you do better than this? Unsorted points. Okay. So, answering a question like can you do better, okay, means that we have to somehow argue against all possibilities, right. All the intelligent people in the world, right. Someone says that I can design a linear time algorithm, then I have to somehow be able to argue without even knowing what that person knows. No, impossible, you can't design anything faster than something. Okay. Which is essentially can we do better means we have to prove a formal lower bound, right. Can we do better? Well, so some kind of lower bound argument is necessary, right. Which must hold against all possible possible strategies of designing algorithms. Right? So, for this particular thing, let me give you an argument that we can't do better than n log n. Okay. So, here is the idea. Okay. So, the idea of, so this is the notation for big omega is the notation for lower bound, right. Okay. So, so we will construct some kind of an input. Okay. So, construct an input x I, y I between 1 and n such that x I plus y I is some constant C, a large enough constant. Now, what does it mean? In this particular input, okay, how many maximal points? So, I will just say this is actually let me not even bother about large enough. You know, everything could be, let us say, between 0 and 1, that is also fine. So, any constant would do. I do not require this. How many maximal points are there? All points are maximal, right? Because from this equation, okay, xi plus yi is constant if we take, so for any pair pi pj, okay, either xi is greater than xj and yi is less than yj, okay, or the other way around, or xi is less than xj and yi is greater than yj. So, no point dominates another point essentially, and therefore, all points are maximal, right. So, if we design an algorithm, I mean whatever be the algorithm for maximal, that algorithm should be able to detect this condition. If it is the correct algorithm, it should produce the final answer. Okay. Now, to produce the final answer, it should have been able to conclude that for all pairs of points, okay, either this is true, either this is true or this is true. What does it mean? It means that it actually must gather information, enough information about all points, so that it knows the answer whether, you know, xi is greater than xj or xi is smaller than xj, because without figuring out this, it will not know whether or not it dominates. So, at the end of the algorithm, whatever be the algorithm for maximal, okay, the algorithm should have gathered this information or deduced this information, which means that we have enough information by which we can compare any pair of points, and therefore, with that information we should be able to sort, and therefore, the lower bound for sorting should apply here. Okay. So, at the end of the algorithm of any algorithm, basically, i.e., we can sort without any further comparisons. It does not mean that, you know, every pair of points have been compared, but there should be enough information in the end, so that if we pick up any 2 points, we should know either condition 1 is satisfied or condition 2 is satisfied, which means that now with this information one can sort. Right. So, it cannot be faster than sorting I the lower bound of sorting applies. So, even this simple algorithm, okay, is actually optimal, because we can't do anything better than sorting, and we know that whatever is the lower bound for sorting in whatever model. So, in the comparison model, the lower bound for sorting is n log n. So, this is also n log n. So, I will just mention one word about the model. Okay. We have not quite actually looked into the model that we are using. Okay. I mentioned in the first lecture that we are dealing with real numbers. Okay. And therefore, we are actually also we have to deal with real valued functions and so on and so forth. In the normal model of computation, we are only dealing with some comparisons, perhaps some addition, subtraction, so on and so forth, but normally you analyze only with respect to comparisons. To do this kind of geometry computing, okay, we have to resort to other kinds of arithmetic operations, which may be even if you want to find the distance, you may have to compute the square root, okay, because the L2 norm, which is the root of the sum of squares, requires us to not only multiply but also take square root. Some of these problems presumably could also depend on something like angle computations. We won't rule it out at this stage. Okay. Right now, I don't want to get too much into the model of computation, but you must keep in mind that the available operations are most of these basic arithmetic real valued functions. Right. So, what exactly we will use, I will come to that probably much later in the course, but I am just making this point. Okay. All right. So, this is a optimal algorithm for finding maximal. Let me also mention another possibility that because I said the techniques that we have learned in other algorithm course can also be applied. So, suppose we have to apply divide and conquer to this problem. Right. So, how would the divide and conquer work? So, let us say divide and conquer. You normally would divide into two parts, okay, solve the problem in the two parts and then combine them somehow. Okay. So, in this particular case, we have a set of points in the plane. What would be a natural way of dividing this problem into two parts? Okay. So, let us go with this, that we project the points on the x axis. So, I am not drawing everything, but some of them, and then after the projection, okay, we can find the median point, and that will partition the point into two parts. So, that is a clean way of partitioning, that there is so one part is completely on one side, the other part is on another side. Okay. Of course, when you do something like merge sort, you do not do this, you actually partition in any arbitrary way. I can just take any n over 2 points and take the complement of those n over 2 points. Here, this way of partitioning is actually by finding the median, I am actually finding a kind of a separator where all the points on one half have larger x coordinates than the other half. Okay. And because this is for maximal, as we had seen in the previous approach, that it helps us to figure out if some point can be a candidate for maximal. For instance, all the points in the left half. Okay. So, suppose this is the median, okay. Then we know for sure that the points on left half cannot dominate any point on the right half, because they have smaller x coordinates, right. So, then if I am trying to solve this by divide and conquer, okay, I find the maximal on right half, I find the maximal on the left half, okay, which would look like, let us say, some staircase here, some staircase on this side, another staircase on this side, right. And somehow we need to combine this staircase, right? And we know that the staircase on the right must survive, right. If it is maximal on the right half, it has to survive. It is only the points on the left half that may be dominated by some points on the right side, and that is also easy to figure out exactly which one by just observing that if you have these two staircases, these linearly separated staircases, okay, because there is a separation between them, then all I need to do is find out what is the maximum for any point, okay, if the maximum y coordinate to the on the right half, okay, is larger than this one, right. So, that means basically I just extend this and all this is not maximal and anything above this is maximal. So, how do we find this thing? Simple, right? Find the largest y coordinate among largest, which is actually this point. We know that it is a falling staircase, and then you compare the y coordinate of all these points in the left half, okay, and filter them out. So, how much time does it take? Order n, right. So, then if I have to write a recurrence, then I can write the time to compute maximal of n points is 2 times the time to compute maximum of n over 2 points, okay, plus big O of n. This is your very familiar recurrence, okay. I am not writing the terminating condition, and that implies T's of n equals. So, that is another n log n algorithm, right. Okay, good. So, n log n is a lower bound and we can't do better, okay. Fine, but let me scroll back to this situation. What happens here? The point, there is only one point that is maximal, right. So, once you have found this point, which is the maximal point, when you compare this point with any other point, it dominates every other point and they go out, gone, right. So, if I have this algorithm that I compare, I find the y coordinate, the maximum y coordinate, okay, and when I do my pairwise comparisons, I always do my pairwise comparison starting with the maximum x coordinate, okay, and then when I finish this, then I take the next point and then do the comparisons from that. Okay. So, if I run that algorithm, it is an n square algorithm potentially, but in this particular situation when there is only one maximal, how much time will it take to run? Just n comparisons or n minus 1 comparisons will suffice to eliminate all other points, right. So, then we have beaten the n log n bound, at least in this one special case. Right. So, of course, you can say that this is only for this one special case, but it does not hold in the general case. Yeah, true, but with this observation, does it give us any hope that there is any further scope of improvement, and how? Okay, so, what I am saying is that faster algorithm when there is only one maximal point. Okay, this is what I just pointed out. Okay. You can actually extend the same argument and say that we can probably design a faster algorithm when there are even two maximal points perhaps, by some kind of a similar argument, right? Because with one point you eliminate everything, you pick up the next maximal point, and with that you may have eliminated everything else. So, again order n you are done. So, what it amounts to saying is that, or so what would you deduce from there? I mean, what is the lesson that we can take from this? Or just not just one, I am saying when there are few maximal points, okay, then there is probably potential for improvement, okay. And of course, we do not know initially whether there are one maximal point or there is one or more than one, or even maybe all the n are maximal points, but it seems to depend on what is basically what we can call the output size, okay. Output size may be crucial. But then I do not know what the output size is. You give me a set of points, how the hell do I know that how many points are going to be maximal? Okay, if I knew that there is only one maximal point, I could run this algorithm by picking up the maximum y coordinate and running that algorithm and getting it, but I have no idea whether how many maximal points are going to be there. Right. So, here is another idea, okay, another algorithm, let us say. And what I am going to do is the divide and conquer that we just designed, I am going to modify it a little bit. Okay, the divide and conquer, what did I do? We took all the points projected on the x coordinate, found the median point, so that we could divide it into two parts, found the maximal points on the right half, found the maximum point on the left half, and then we merged them, and the merging was very simple. Now, instead of actually finding out all the maximal points on the left half, which seem to be kind of a wasted work, because some of these points are not maximal in the final output, right. Even before I compute these maximal points on the left half, if I could somehow find a way of filtering them out, okay, then I would not have to actually do it recursively. See, the reason we got this n log n kind of thing is because we had to write down 2 times n over 2. We solved the right half recursively, we solved the left half recursively. Now, what I am saying is that instead of actually solving the left half recursively, okay, if we can somehow find out what the maximum point on the right half is, and just use that to filter out this, okay, then perhaps there is some savings, okay, and of course, we have to analyze how that saving is going to happen. Okay. In other words, when we have these points, okay, suppose this is my median line, I would the final so I want to find out that to the right of this median line, okay, what is the maximum y, what is the maximum y coordinate, okay? And for that, do I have to sort? No, right. I only need to find the median, which takes order n time. Okay. By the way, I forgot to mention that, so this order n term not only contains not only has the component for merging, but also has the median, finding the median, right, median plus merging, it has both these components. So, I can find the median in linear time, okay, and after having found the median, I can separate out all these points. I need not know the the relative ordering of those points. I know the right half of the points, and once I know the right half of the points, I can find the maximum y coordinate, right. If I can find the maximum y coordinate, the whole thing is order n. So, in order n time, okay, I know essentially what is the maximum y coordinate to the right, which amounts to saying that I actually know where the staircase is going to cross this median line, because the shape is such that it is a falling staircase. So, essentially what we know is that the median line is going to intersect the staircase here. Okay. So, we have actually computed some part of the output, because this thing, let me use red. So, this thing actually is a part of the final staircase. Okay. Now, once I know this, okay, then all these things basically disappear. Right. So, all these things basically disappear, and then I continue doing the same. So, I know this information, okay, and of course, with this I can also maybe eliminate this some points here also, that is fine. I can eliminate these points also, and then I have to find the remaining staircase. I have to find out what is the remaining staircase, which is basically something like this. So, I have to now compute the staircase here to right and compute staircase to left, and whatever I compute, the left staircase that I compute will survive. Okay. That is the beauty of it. Now, I do not have to do any merging, I just stick them together. It is like something like the quicksort, if once I have found the partitioning element, okay, I know the points larger than that, I know the points smaller than that, and I just paste them together. I do not have to merge like you do in merge sort. So, Similarly, here I do not have to actually find out whether the left staircase will survive. It will survive. I simply have to paste it together. Okay, so that becomes trivial. All right. So this is the algorithm. So I compute. So I just write down the steps. Find the median. Okay. Then find the intersection of the staircase with median and eliminate all points below it and to its left, okay, and then compute staircase of left, compute the right staircase, yes, and that is it, you are done. Finally, the output is simply just joining these two staircases. Fine, it is easily stated. You can also write a program. The challenging part is how do you analyze this? What can we write? I mean, when you have to analyze this, what do we write? So T's of n is the time to compute the entire staircase, okay, and that is essentially the order n that you require for finding the median, okay, finding the where the staircase intersects the median, okay, and then T of n L plus T's of n R, left hand side, right hand side. Right. All we know is that n L and n R both are of them are less than n over 2. But then we do not know exactly what the values are. We do not know what the values are, and that is what actually complicates matters. If you do not know what the values are, then if I write T's of n over 2 plus T's of n over 2, we are back to this thing. Okay. So there is something else that should come into this, right? Something else that should come into our calculation or analysis, and our intuition was that it has got something to do with the output size. Okay. So this recurrence does not capture anything about the output. It is still talking about the set of input points, n input points, okay. And then again, when we are doing on the left and right half, we are only applying the recurrence to the points that survive in the left half and the points in the right half. Right. We have nothing more than so this is the best that we can do if we write the recurrence in terms of input. So somehow we will have to bring in the notion of output here. Okay. So for that, I will do the following. I will say, suppose H is the size of final output. Okay. H is not known. We do not know H. Okay. But then I can maybe just say if the running time is a function of both input and output, I should actually now make my recurrence a little bit more complicated. So time for input size H, sorry, n, and output size H. Right. So this again the order n term remains order n. Okay. But now I can say something like T's of n L comma H L, let us say, plus T's of n R comma H R. Okay. And then what do we have? Yeah, I surely have this condition n L and R are both less than n over 2. Okay. There is something more I can say about HL and HR. What can I say? Yeah. So, HL plus HR, okay, equal to H minus 1, because we have found one stair, one stair of the staircase. Now, this recurrence, okay, if you look into it, I maybe I should actually ask you to try to solve this, okay, but I'll give you the solution, okay. Now, how you solve this, you take it as an exercise, okay, how you're going to solve it, how does one solve such recurrences. The solution to this happens to be how you are going to verify this, I leave it up to you. How do you solve? You may not have seen such recurrences before. All right. Now, if you look closely at this solution, n log h, okay, what is the maximum value of h? N, right. So, the maximum running time is n log n, which is what we found out even by doing this lower bound argument, and also the other algorithms give us n log n. When h is small, for instance, h is constant, this is order n. So, it interpolates nicely between all kinds of output sizes, small to large. All right. Not only that, you can also show, this is something that is outside the scope of the discussion right now, can be shown that this is optimal with respect to input and output. Output sizes. Okay. So, we will stop here today.